Huh? Something crazy out there. Okay. Joe's gone today? No, other Joe, Hodgson, but thank you, Joe Cow. Yes, I do see you. And Ariman's gone. But other than that, everybody's here. Okay. What did we learn on Friday about vectors?
They represented by an arrow, both distance and magnitude.
There you go. So we have despicable me, both direction and magnitude. We talked about a line segment, not a ray, because it has like a finite length. We talked about which of these was more technical, and it was this one, right? I briefly introduced the idea of rectangles being used to put multiple vectors together, and who, from the very, very, very end of Friday, that means. Yeah, kind of like a combination of both, or putting it all together. Usually you see it in like businessy things. When you're dealing with net cost or net profit, it's like putting it all together. The overall effect. Net profit would be you made money, but you had to spend money on like supplies or on workers, et cetera, et cetera, et cetera. So net profit is what happened at the end, what the overall result was. This one, hopefully, out of all of them, makes the most sense. Because do you guys see these two different forces, one on top of each other? And then what's the net? The whole thing. You see it? But what's trickier when they're not in line with each other? What's trickier? Well, do you guys actually know, what if this one was flipped the opposite way?
Then it would be half of that.
It'd be subtraction instead of addition. So it's adding because they're both going the same direction. So this much in this direction plus that much in that direction is the overall. If this one was flipped around, it'd actually be subtracting. That's a little idea of vector addition versus vector subtraction. But what's trickier about these three, and why aren't they as straightforward as this one? The vectors are, let me put it this way. So when they're at an angle to each other, in a sense, we can think about, well, let me take, what do I want to use? Let's use this one, I think. Let's use this one. Every vector we're going to see today, and we're going to continue seeing it tomorrow, every vector can actually be made a triangle. Every vector can actually be made a triangle. With gravity, it's a little bit hard because gravity is straight down. It's not at an angle. But technically, we could actually make this little blue guy, if I can get my orientation right. Give me one sec. I didn't quite get it perfectly set up this morning. It's going to mess us up today. But every vector can be split up into horizontal and vertical components. Quick example. A silly example. If I was to tell you right now to head to home plate on the softball field, right now, and I won't, it's raining, but if I was to tell you to go to the home plate on the softball field, where would you be headed? Oh dear. Yeah, that way. Okay. From right here, is that a straight line or is it a diagonal line? Okay. What do I mean by straight? Oh, that's tricky. Isn't it a straight diagonal line? Well, maybe not a straight diagonal line. You might hit a few walls in between, right? Okay. But in some way, shape, or form, we could like take a picture, like an aerial shot, and then show with a diagonal line from me to the home plate, right there, right? Okay. That's kind of like a vector in the sense that vectors are diagonal. They're showing the overall, like where are you headed, where are you going, where are you pushing. But in reality, to practically get to home plate, should I follow a straight diagonal line from right here? No, it wouldn't be wise. Now, it might happen to be that I might make it out that door okay. Like I might be able to hit that diagonal line, but if I kept on going in that diagonal line, wouldn't I bang into the wall on the other side of the hallway? Right? Okay. And I can't walk through walls, so I'm not going to do that. What's more practical than following that straight diagonal line? To go, well, yeah, to turn through the door and then turn again and then go out and then turn again, then probably go up the stairs unless you want to hop the fence. And then, right? So there's a combination of different ways of getting there, not just the straight diagonal line. Have you guys ever heard the phrase, as the crow flies?
No.
Not at all? Okay. If you were to look up on GPS right now, how to get to like your house, for instance, what's it going to give you?
A bunch of different.
But isn't it going to give you like a distance? What is that distance?
Straight line distance after.
What's the distance through that?
It's the distance through the route that you're going to take. Like you're supposed to take this many miles and this many miles and then like this many miles, and usually it's 0.3 here and then 0.2 there and then turning in all this jazz. But what it's added up, when it says, for instance, my home is, oh, what does it say? I should have this memorized. I think it's 12 point something miles away. But the drive is like 45 minutes. But either way, when it says however many miles away I am, that's the route that I'm taking. But what if a bird was going straight to my house? The bird goes up and it just goes over, right? Does it have to worry about all of this? No. So the crow flies is like, okay, what's the actual distance diagonal line from me to my house, which would be there-ish, just way over there-ish. Okay. As the crow flies, the overall effect, but it might have all these pieces in between as far to the route that would make it longer. Okay. It's kind of the idea with vectors, because with vectors, not only can each individual vector be broken down into smaller pieces, but all those smaller pieces can be added up to see the overall effect when you combine multiple vectors. I might not go too crazy into this, besides the fact, if I was to show you guys something, okay? Let's say I had, and we're going to see this before the end of the section, and some of you might have already seen it. If I had like a box, I'm putting like a center of gravity on the box. If I had a box on a hill, and let's say even worse, it had wheels on it, okay? What's going on? You actually have gravity pulling it straight down. And we can say gravity combined with weight. Some of you in physical science have at least heard a little bit the discussion of gravity and weight and how they work together, etc. But we have a force pulling straight down. We actually have a force, like if there was a poor little mouse underneath this box with no wheels, how healthy would the mouse be? Because there's force against the hill too. Like, yeah, there's gravity pulling it straight down, but there's also force against the hill. Like, there's actual pressure on the hill itself. And then we have this force that is ultimately pulling it down. But if this was actually stationary on the hill, there must be something, whether it's a trailer that's holding it, whether it's a person that's pulling it. And so usually we can show it going the other direction because someone's trying to keep it from going down the hill. But there are multiple forces going together, not just one, not just two, but three. There are other diagrams that are a little bit harder, where you might have one single object. You might have multiple vectors that are working on it. You're going to see things having to do with like jets or planes trying to go a certain direction, but a wind that's like coming against it. And so it's possible you might have actually more than one or two forces, but you might have three. But the trick is, if you were to have multiple forces and you were supposed to add all of these together, we could call them like vector U and V and W. We can name them different things. But if we're trying to put them all together, the geometry gets way harder because we actually have to, bless you, we would actually have to put them so that one runs into the other so we can see the combined effect. Like on your GPS, if you were to follow one direction, and then decide to follow another direction that was from like 4 steps in the future, could you have some issues? If you were to be given the direction separately and say, okay, well, I want to turn, whatever you want to say. I want to go north on Woodley. No, actually, I want to go west on the 118. No, actually, I want to go, like if you were to take those out of order, or if you were to do them separately, it doesn't help. What you need is them in order, saying do this first, and then that, and then that. So with vectors, even though we can look and say, okay, all of these are components, or all of these are important to the overall picture, in order to see the combined effect, we would actually have to draw them each one at a time in like a succession so that we can say, okay, first and then second, and then we have one more, right? And then third. But here's the hard part. My net force would combine this guy with that guy from the very beginning to the very end. That would be my net force of this hypothetical situation I was talking about over here. Do you guys see a triangle? Good. The problem is, Matthew's saying, I see a trapezoid, and I'm like, well, maybe if those two are parallel, but we're not even guaranteed that. Diagrams that only have 2 forces, if I was to go back to our roller coaster, these ones are like the basic ones, because basic triangles we can solve. Now, what if it's a right triangle? Do we have stuff for that?
Yeah.
What if it's an oblique triangle? Do we have stuff for that now? Law of cosines, law of sines. So if it's a triangle, we'll be good. But if harder vector diagrams actually have more than two forces, all of a sudden we might have multiple sides, and all of a sudden we don't have a triangle. So ultimately, even though there are those really cool vector diagrams where you could put them head to tail, and we'll practice them a little bit, ultimately what's going to be easier for us isn't thinking about the geometry of it, isn't going to be thinking about law of sines and law of cosines, even though that's possible. The easier way to think about this is how Joe said it. And I asked, do you see a triangle? Most of you would have answered no, but Joe says, or said, I see lots of triangles. Couldn't this, instead of being a diagonal line, be an over and up? Where you have to go, say, due west and then due north instead of going diagonally, kind of like my example to get to home plate. Maybe I don't want to go on a diagonal line. And then couldn't this one have been going west and then going south? Same thing, instead of the diagonal line, I could go right and I could go down. Couldn't this one be going over and going up? Now this one's a little tricky because I tried to draw it due north, which means, is there an over? Nope, there's just an up. But here's a question. What if I was to figure out this length and call him A? And I was to take this length and B, and take this length C. Could there be a way of taking each of these little baby pieces and finding the end? What do you guys think? A plus B minus C? If I could play with my little right triangles, maybe it's not too bad to get to the end without having to figure out who this shape is and what his lengths are, what kind of formula could possibly relate. Maybe it'd be easier to say, I'm going to use triangles for every single vector. And, well, hold on. I needed A plus B minus C to get here. What am I going to have to do for here? A D and make that an E? Got it. So we are going to be learning how to properly deal with vectors by themselves, first of all. If you guys notice, the beginning of notes just has one vector, just one. We're going to be talking about just one vector, but for the purpose of building up to being able to take a situation where we have multiple vectors, and at least getting a basic understanding of how to put multiple vectors together, which will probably be easiest if we break each one down into their own or its own individual, what we call components, its own little baby right triangles, its own little baby horizontal verticals. We will talk a little bit about how it's proper to put together these little triangular vector diagrams, but once again, if it gets harder, we don't have triangles anymore, at least not the big picture, so it would be easier to make little baby right triangles. That's just giving you guys a peek as to what we're doing, but first of all, let's figure out how to deal with one vector, just one. Just one. We already wrote down on Friday, and I could go back to the picture. You guys just saw it again. But we can name a vector by a lowercase letter and make it bold, which you're not going to be doing in your notes. What are you going to be doing instead of making it a bold letter? Putting the little arrow on top. Good. The little vector arrow. We could call it by a lowercase bold letter stop, put an arrow on top. Or we could call it by its initial, then terminal points. Its beginning and then ending. And we talked about how we couldn't call this vector QP, because if it was the vector QP, it'd be going the opposite way. So that's another way of naming the vectors from the beginning to the end. And remember, once again, vectors don't go on forever. We did briefly mention how each point, the beginning and the end of a vector, does or will have an x-coordinate and a y-coordinate. But what we didn't talk about is how I was able to, like in the picture that you just saw, take three vectors that were drawn from the exact same initial point and be like, it's not a big deal. I can move one of these up here, and I can move one of these over here. Oh, wait. I shouldn't move both. We didn't talk about how I was allowed to move this one and I was allowed to move that one. Usually when you have graphs of things, guys, are you allowed just to move anything any place you want it? No, but forces are different. And just think of the reason why. Remember how we were talking about roller coaster cars? If you're here in a roller coaster car, is gravity acting on you? Yeah. If you're here in a roller coaster, like upside down the loop, is gravity acting on you? How about here, is gravity acting on you? Gravity is equal wherever you draw it, because Wherever you are, gravity is pulling you straight down. And Joe, we're not going into the atmosphere. So gravity is going to be the exact same, which means it could be here on this car or here or here. What has to be true? Gravity needs to be pointing straight down and have the exact same numeric value. So that's what's going on in the second page of notes when we start talking about equal vectors. Now first, real quick, magnitude, we talked about it a little bit on Friday. Magnitude is the how muchness. Since vectors have like an actual number attached, the vector won't go on forever. There's an actual length, and the length could be, I went 5 miles this direction. That could be a length. But it could also be I was going at a speed of 40 miles per hour. That could be the length. There could be 40, but it's denoting like a speed or a force. Always just distance, or aren't always just measuring distance. But there is going to be a numeric value to every vector. It's the how muchness. You guys know like magnitudes of earthquakes, right? How great they are. Same thing for a vector, kind of how great it is. Notation for magnitude. You could do the double lines of the PQ vector. You could do the double lines of the little lowercase v vector. And there is a formula for magnitude, but we'll get back to that in just a little bit. Well, no, let's go ahead and do it now. Because we're talking about single vectors. If you have a single vector v going from a p to a q, you have a single vector v going from a p to a q. And if I just brought up the idea, and Joe kind of helped me, that every vector can actually be shown as a right triangle, if you don't know the magnitude, you can also say, I don't know the hypotenuse. And if I don't know the hypotenuse, if I knew the sides, what could you do? So if they were to ever give you the components, or the over and the up and not the diagonal, you could always find it using Pythagorean theorem, which would say the hypotenuse squared, or if we're talking about the length, it would be 2 double lines showing magnitude. The length of the vector, not just the name, but the length, always having double lines, would be the square root of a squared plus b squared. That's pretty much the most common formula for magnitude. Now, sometimes they just give it to you and say the magnitude is 10. You're like, sweet, thanks. But if they don't, if you know the components, if you know the horizontal, vertical, you could find the magnitude yourself if you just could visualize it as a hypotenuse. That's a formula that's pretty important that we're going to be using a lot. Okay. So talking about a single vector, how to write it, how to denote or how to show its magnitude with this double, like it looks like double absolute value lines. Just the how muchness can be a hypotenuse. Down here, equal vectors is what I was just talking about how gravity can be drawn at many different places in like a situation or in a picture. As long as I keep the vector with the same magnitude, the same length, and the same direction, the same angle, technically I can move it around because it can be acting in different places. And when I do vector diagrams, if I need to show the combined effect or the progression of one vector to another, I'm going to have to move it. This is what makes it legal. You're allowed to move around vectors as long as they stay equal, which means same magnitude, same direction. So if we had an example, like the next page, I can probably dual page it for a second. I see a few of you guys still writing. And if they were to ask me to show that these two are equivalent, they're telling me they are. They're telling me they are. But they're asking me to mathematically prove they're equivalent. They look equivalent. They look the same angle. They look the same length. But let's not get out protractors and let's not get out rulers. How can we mathematically talk about length and or angle? We wouldn't want a similar triangle, Joe, because remember, similar can be different sizes. That could mess us up. Try to go for congruent triangles. Can we make both of these triangles, guys? Okay, so we can go down, down on him and over. We can look at the triangle and see if they're congruent triangles. Because if they are, the angles would be the same and the sides would be the same. So let's think about that. Okay. If we were to look at this bottom guy, PQ, from 0, 0 to 3, 2, do we know his magnitude right now? No. But we could know from 0 to 3 aren't we going to have to do like an x displacement or a change in x by 3? And then to go from a y of 0 to a y of 2, aren't we going to have to go up 2? You guys tracking?
That's 9 degrees.
9 degrees. Hold on. I'm asking for length, Joe. So magnitude, we could say the magnitude of u is going to equal, if you draw your triangle, guys, how do we find the hypotenuse? Pythagorean theorem. Good. So 3 squared to be 9 plus 2 squared to be 4. And remember, that's c squared. So what do we have to do? Square root of 9 plus 4 is square root of 13. We have found how long this vector is. We could even do, and I think maybe, Joe, this is what you're doing, we could even find the angle too, because couldn't we solve the right triangle saying we have opposite and we have adjacent? Hold on, which trig ratio, since we're in a right triangle now, which trig uses opposite and adjacent? So I could do tangent inverse of 2 over 3. Someone in degree mode, go find me that one. But as you're finding me that angle, we can't stop at this vector. We have to show this guy is the exact same. So let's go looking for a vector v. Now hold on, vector v is not at 0, 0. So how can I use his points? 1, 2, 4. How can I use his points to try to figure out what's going on? The change, good. The same way I was talking about the change in x's down here, I can find the change in x's up there. So I can do the change in x's, 4 minus 1 squared, plus the change in y's. Wait, is there a special formula? Looks like x2 minus x1 squared plus y2 minus y1 squared. Oh, distance formula. It's where it comes from. A couple times this year. What ends up happening when you do 4 minus 1? How about 4 minus 2?
2.
Oh my goodness. Lengths are the exact same. So far so good. The magnitudes match. The angles, because I would do the exact same thing of tangent inverse the change in the y's, which we found to be 3, over the change in the x's, which we found to be 2. 4 minus 2, and then the change in the x's. They both end up being 2/3. And so actually, regardless of what our calculator tells us, it's going to be the same angle. But what did you guys get when you plugged in tangent inverse of 2/3? 0. Thank you, Joe. This one would be the exact same. So here's the idea. Despicable Me. Was it right when it said that a vector has both direction and magnitude? Yeah. But the sad thing is when these pictures or these application problems get harder, it's actually going to be a lot easier. Instead of talking about vectors in terms of magnitudes and directions, to talk them in terms of either their points, their beginning and their ending points, and or their components, how far over and how far up. It's going to be a lot easier to deal with them that way. But we're going to have to kind of deal with both. So let's talk about those components. We were just saying, just to show they're equal, just to show that they are the same length and the same angle, we had to break down and figure out change in x and change in y for both the angle and the magnitude. So let's talk about that. Component form. Breaking a vector down using its points. Magnitude and direction isn't bad. It is the big idea for vectors. But if we have these nasty pictures coming that are combining lots of forces, and we're only going to see the basics in pre-calc. Physics would get a bit harder. Calc 3 would get even harder. But just the basics in vectors. But preparing you for what might come. It's going to be a lot easier to break vectors down, or at least be able to. So kind of putting together things that we just saw, we can break SU into its components, aka into its horizontal change and its vertical change. We're going to start off basically just talking about lengths. You saw me just a second ago putting arrows on those lengths, and those arrows are important, but for right now, just talking about lengths. What did you just see me do when I was looking at the 2 points, the beginning and the ending of a vector, when trying to find the horizontal and vertical difference or displacement? What did you see me do to figure out how far over?
x2 minus
x2 minus x1. Good. Why do you think I labeled him x2 and him x1? Good. This is the initial, this is the beginning, so he would be the first point. And then S is the ending, the terminal, we would call him. That's the second point. And what do you see me do, or what do you think we could use to find the vertical displacement? Y. Y2 minus Y1. So this builds us up to another way of showing a vector. We can show a vector not just by a picture, not just by a length and an angle, but we can also show a vector using these side carets. Now, you've used them before for like greater than, less than, but I'm using it more as a parenthesis or a bracket. Side carets, we're going to actually say we can take x2 minus x1, y2 minus y1, which will end up getting us some sort of, I'm going to call it A and B, but I'm also going to show you what the book might call it. I like A and B because it makes it simpler in my head. You can subtract those two and get an A, which is a length, subtract these two and get a B, which is a length. But the book might also say something like, hey, you know how he can be called RS? Do you remember how he can also be called V? The book would be like, well, there is another way of writing it. You could call this V1 and V2. I'm going to put that in parentheses because technically I think it's a bit more confusing. But when they say V1, V2, what they're really meaning is this horizontal change, which I'm going to call an A, and this vertical change, which I'm going to call a B. It's really just lengths. It's not a big deal. It's how far over and how far up or down. And so once we see that we can write vectors like that with these little side carets, then comes the quick reminder of the magnitude formula that we've already written down, we've already highlighted. But just a quick reminder of, if that's how you can always find the horizontal vertical components, instead of just doing a squared plus b squared, we can actually say, okay, subtract the 2 points, x2 minus x1 squared plus y2 minus y1 squared, which, as some of you guys have already said, is basically the distance formula. So if you guys are doing like the whole highlighting thing, components are specifically the side carets with the horizontal and vertical displacement showing the vector from beginning to end, how far over and how far down. At the very bottom, it says something like there can be this guy called a zero vector. And the zero vector is kind of awkward because he doesn't go anywhere. So it could literally be 0, 0. And it couldn't actually be anything else, because if I put a 1, 1 or a 2, 2 or a 3, 3, that means going over 1, going up 1, going over 2, going up 2. The only zero vector is going to be the one that says I'm not going over at all, and I'm not going up and down at all. So it's not at the point 0, 0, it's moving 0, 0. It's not moving at all this direction, it's not moving at all that direction. So the zero vector is actually just a point. It's kind of boring. A unit vector is one, well, I can't really tell you what his A and B would be, because it could be all sorts of different things. But I can tell you that his overall magnitude is 1, which means when I take his components and when I do the formula for his components, a unit vector has a length of 1. We'll talk more about unit vectors as we go on, because they get to be a little tricky if we're trying to find them. So components. The long story short, if you want to give yourself like some sort of reminder of what we're doing, we're basically breaking a vector down into a right triangle. Basically what we're doing. We're saying, great, you're diagonal, good job, but I want to know the steps to get you. I want to know the horizontal steps and then the vertical steps, whether I'm going to the right and down, to the left and up. I want to know the steps to get to where the diagonal vector is showing. That's like the silly way of talking about it. Let's see if I have an example. Perfect, I do. Okay, this guy, I haven't named his points. Give me 2 random letters from the alphabet. Go.
T.
T and
J.
TS. Can I put the S first and the T just because of alphabetical order? Okay, so vector, ST, for street, I don't know. So vector ST, I see him. But how could I write him in component form? 3?
Yeah.
Let's check Joe. Does it go up 3?
No. It's -3.
Ah, don't we have to go left? Good. The first one we need is the x2 minus the x1. Wait a minute. Did I do it in the right order? You guys might need to write yourself some little note that you need to do the terminal point minus the initial. Who's the terminal side for mine? Or who's the terminal point? Is it S or is it T?
T.
There you go. When you're doing terminal minus initial, I'm not allowed to do them in any order that I want. I have to do them in the right order. So some of you, it was a little too small, but the arrow is actually up here, which means my final x would be -1 minus my initial x was 2. My y, my final y is 4. My initial x is 2. Does it make sense that the vector from beginning to end went -3 and then +2? Now the way I drew it doesn't really make sense. Let me draw it another way. That was the right or correct right triangle. But if I did it the way that it showed, going left 3 and then up 2, does it also work? Yeah. So the positive, negative also shows you direction, like where you're headed. Now, any part of this vector at the point -3, 2. -3, 2. No, this isn't a point. This isn't an ordered pair. Remember, it's a change in y. Did the x's change by subtracting 3? Yeah. Did the y's change by adding 2? Yeah. So be careful. Your brain's going to have to figure out what this component form is. But this component form is showing us the movement or the change, the horizontal and then the vertical. It's not giving us an ordered pair. It's actually denoting movement or change. Okay? That's component form. But what else? Ooh, can you guys read the directions even though they're small? What else were they asking besides component form, which we just found? I want you guys to ponder magnitude and see if you can find it for me when I answer Priscilla's question.
Are we going to get to 0 tomorrow?
No, tomorrow. Chapel day schedule. Sorry, kid. It's a good question, though. Thanks for the heads up. When you guys come in tomorrow, go ahead and grab correction papers in the back for your group. How would we do magnitude?
A squared plus B squared.
Oh, yeah, that's right, because they're just asking for the length. So if we have the legs, we can find the hypotenuse just by square rooting -3 squared plus 2 squared. You guys already figured out it's 13 again? Good. Magnitude is easy if you break a vector down into its components, because it's like, hey, that's a leg and that's a leg. Perfect. Plug it in. Basic operations. Now we have to go beyond just dealing with one vector. Now we have to at least start talking about what if things are changing, whether in like a situation, whether in a problem, whether in multiple vectors being put together with addition or subtraction. And we'll just see the basics today, which is totally fine. I have pictures down here so we can talk about it too. Actually, let me move this guy over here. I'm not sure he's way over there. There we go. Okay. What if I was to call this guy vector v? We can call this guy vector u. Okay. Scalar multiplication. What if you ever see, oh, it's a bold. Make sure you put little arrows above. But not the components. They're just lengths. He's the vector. What if you were to see something like, we want to go ahead and multiply this vector by a constant. I'm just going to use the letter A. I want to multiply a vector by a constant. In a practical example, that could be something like, okay, they give us a vector v, and they say vector v is equal to, I don't know, what could that be? -3, +3 maybe? That could show this vector if I go over 1, 2, and 3, and up 1, 2, and 3. Okay. If they were to show this vector, negative 3, 3, and they were like, okay, I want to find double this vector. If ever they show that, what they're actually asking for is all they want is this vector to be double its length. What do you guys think happens if we double the length of a vector to its components? Yeah, but how much larger? Instead of going negative 3, we're going to go negative 6. Instead of going positive 3, we're going to go positive 6. We're going to double the components. It's as easy as that. So if we ever have to do scalar multiplication, you're just going to take whatever constant's being multiplied and multiply it by the first component and then multiply it by the second component. The only time that gets weird is if there's a negative number, like negative 2 times a vector or negative 3 times a vector. Any ideas what's going to happen if there's a negative? Not shrink, actually. That would be like a 1/2 or a 1/3. Negative switches the direction. The arrow would be going the opposite way. Vector addition, now this one gets a little bit trickier, unless you use our idea of baby triangles. We'll see the picture tomorrow when we come back in. But the math, just because some of you might want to get a little further in homework than others, the math is easy if you have your components. Just like we did with A's and B's and C's, the math says just add the horizontals and add the verticals. No big deal. The picture is what gets tricky. All right, cool kids, I'll see you tomorrow. Keep on being inspired by Despicable Me. Zoop, 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 zoop.